Okay, so today we are going to look at file systems, and this is going to be the last key component of an OS that we cover in this class. This slide here shows us what we have done so far and where we are. So our first big component was looking at processes. We looked a little bit at threads and saw how the OS provides the abstractions of processes and threads and then maps them onto the CPU. It's a way to manage the CPU. We looked at address spaces and memory management, which was a way to manage the RAM on your machine. And today we are going to start talking about files and file systems, and the hardware resource that the OS uses to manage files and file systems is obviously the hard disk. So we are going to look at several key functions that a file system provides us, which include naming, how files are named, protections, how do you enforce protection across between files and users. We'll look at persistence, how data is made to persist on disk across reboots. We're also going to look at how the OS and the file system provide fast access to files on the hard disk. Now, designing a file system involves two key components. The first is how your data, which is your files and folders, are organized and stored on disk. What are the on-disk data structures that are used to lay out the files on disk, provide access to these files at a later time in an efficient fashion, and so on. So that's all on-disk layout and on-disk data structures. Now, the file system is also a piece of code that is part of your OS. In most monolithic kernels, the file system code resides inside the OS, and we'll see in UNIX it resides in user space. But regardless of where it resides, the file system also implements in-memory data structures that allow you access to the on-disk files, and it implements all kinds of interfaces that both users, processes, and users themselves use to get access to their files. So designing a file system involves both of these components. How are you going to lay out your data on disk, and how are you going to implement the file system code itself in the OS? We are going to look at both of these components. Today's class is an overview of general concepts, and then next time we are going to look at how UNIX is going to implement these concepts. So I'm going to start with the second point first, which is how the file system is implemented in the OS, and towards the latter part of this lecture we are going to look at on-disk data structures for the file system. So this slide here shows us a picture of what kinds of abstraction a file system provides to its user and how it actually maps into the OS itself. Now you will see some similarity between this picture and what I had shown you in the previous class when I talked about I/O systems and device drivers and so on, because remember that the file system and the hard disk is also related closely to I/O subsystem within an OS. So you will see two components here which should already be familiar to you. You see that there is a device interface which provides access to the hard disk, and that's done through a device driver, as we saw last time. In case of the disk driver, there are interfaces that allow you access to a disk, which include reading, writing to specific blocks on disk, and so on. And there are interfaces that are designed for magnetic hard disks. They no longer apply to modern disks, which are solid state disks. They don't move. But if you have the older style magnetic hard disk in your machine, you still have interfaces like seek and so on. And then above this layer is the device independent layer, which is now abstracting away some of the lower level details of how disks work and just providing a higher level abstraction to users. In this case, the abstraction is one of a file, because the file system is implementing that interface for us. So we have things like opening a file, closing a file, reading, writing to files, and so on. And then this interface is also exposed through a system call interface to application processes. Then you might have libraries that provide a still higher level interface to application processes as well. So let's start first with trying to understand what are some high-level design requirements on accessing data. So from a user's perspective, we want any data that you store on your hard disk to be persistent, which means that the data should stay there across reboots. Remember that memory is a volatile storage medium, so we do not have this requirement on anything stored in memory. It's assumed that whatever is in RAM is going to go away if you power cycle your machine, but that is not the case for a disk. Whatever you store on your disk should stay there. So when you implement a file system in your final project, you will have this key requirement, which means that if you shut down your virtual machine and the OS that's running inside the virtual machine and restart it, all the data that you stored on your file system that you implement should still stay there, it should still be available. So that's the first requirement. The second requirement is speed, which means that the data structures that you use to access data on your disk, or in this case access files, should be efficient, should allow you to access this data efficiently and quickly. The third is size, which means that you want the ability to store lots of data on your disk. You want the ability to create large files on your disk. So there should not be any restrictions on how much data you can store or how large the files could be, with the caveat that of course you cannot store more data than the size of your disk, but you shouldn't have, to the extent possible, limits on file sizes. For example, your files should be your file system should support large files to allow you to store things like videos or other kinds of large files on your disk. Sharing and protection is the fourth requirement, where we want users to be able to share their files with other users in a fine-grained manner. So you should be able to, as a user, tell the OS that certain files can be accessible to certain users or certain groups of users, but others are not. And last but not least, you want ease of use, where you should be able to get to your data at a later time and modify it and so on. So we'll go through some of these concepts in more detail in the rest of the lecture. So now let me also say, given those requirements, what's the division of labor? Who does what? So from a hardware's perspective, it's going to provide us persistence because disks are a non-volatile memory. Whatever you store on disk stays there across power cycles, so you get persistence from disk. You get speed also from disk because disks support random access, and this is true for both magnetic disks, where you can go to any location on disk and retrieve data, as well as solid state disks, which only support random access. Size is also a requirement that your disk support, because disks just keep getting bigger. Typical disks now range from anywhere from hundreds of gigabytes to a few terabytes, and that's just one disk. Even on a laptop or a phone might actually have hundreds of gigabytes of persistent memory. Now, as far as OS is concerned, it is also going to provide us persistence by providing redundancy to allow us to recover from failures and so on. It's going to provide some of the other requirements that I mentioned, which is sharing and protection by using things like protection bits or access control lists that allow us access to files. And it's going to provide ease of use through many different mechanisms. So for example, files will have names that are human readable. Internally, files are actually represented as integer IDs, but that's not something users can be expected to remember. So users are given abstraction of file names, and the OS actually maps file names to the internal IDs. And a user can pick whatever name that makes sense for a file. For example, project1.c tells you that this is a C source file that is related to project one and so on. And furthermore, you are also have the abstraction of folders or directories where you can group related files in one folder. So all of these concepts allow you ease of use. And modern file systems also allow you search feature. So even though you may have a well organized file systems, because you have lots and lots of files, sometimes you may not remember where the file is located. So you might have a search feature in OS X that's called Spotlight, and Windows has a desktop search and so on, that allow you to search your file system. So you can not only search for file names but also search based on contents of files and then get access to your data. So with that background, let's now start looking at files and the interfaces provided by the file system to access these files. So a typical definition of a file is that it's a named collection of related information that is recorded on secondary storage. All that means is a file actually has a name which is assigned by a user typically, and it has some related information. So it might have blocks or lines of code or whatever you put in a file that's related, which is why it is stored in this container called a file. And it's stored on secondary storage. So it's essentially, from the user's perspective, that is the logical unit of storage. Although underneath disks use blocks to store data, from a user's perspective you don't see blocks, you only see files and directories. So from a user's perspective, the smallest unit of data that you store on a hard disk is essentially a file. Okay? Files could contain source code or binary data, so it could contain programs, binary data and so on. They can be structured or unstructured. Typical example of Unix file systems is one where you assume files don't have a structure that the file system knows about. Even though the file may have a structure, the file system does not care about it. It just sees files as a sequence of bytes. But there are file systems that are related to database programs that mainframes implement, where they impose a structure on a file. So you could say a file is a series of records or a series of objects that are structured in some format. But those are more special purpose file systems, and most Unix-like file systems just assume that files are not structured. Now files will have other attributes such as a name. I already mentioned that. They may have a type. And again, depending on the file system, you may or may not care about the type. Certain file systems don't assign a type to a file, which means that you don't actually know what type of a file it is, but other file systems do. So they might say that this is a Word document, or this is a source code, or this is a binary object, or it's an HTML file. So the file system actually knows the contents of a file. And there are different trade-offs based on whether you use the file type as a key attribute within the file system or you're oblivious of the file type. And you may have other attributes like location, size, protection, time of creation and so on, and we'll get to some of these. Now coming to the interface that the file system exposes, these are typically exposed to users through a system call interface. So for accessing a file, we have familiar operations here like opening a file, closing a file, reading a file, writing a file, creating and deleting files and so on. Right? And then there are operations that allow you to change the attributes of the file, and attributes are also referred to as metadata. Okay? Metadata is essentially data about the data. So you can change the attributes of a file such as the protection information, the owner of a file and so on. And then there are interfaces like get attribute, set attribute that allow you to either read or change the attribute, as well as some other interfaces that we'll talk about that allow you to create hard links and soft links. Now I'm going to go through some of this material rather quickly because it is supposed to be a refresher from undergrad concepts on OS. And next time we'll actually look at some of these in more detail in the Unix context. Okay. So let's start with the data structure that an OS is actually going to maintain, or a file system is going to maintain within an OS. So there are two key data structures that a file system maintains, which are essentially two types of file tables. There's something called an open file table, which is shared by all processes, and that basically there's one entry for each open file in the system. And so this table tracks all files that are currently open by all processes within the OS that are currently accessing files. And so since multiple processes can also open the same file for reading or writing concurrently, you will have something called an open count that tracks how many processes currently have this file open for reading or writing, as well as several other things like the file attributes, location on disk, pointers to location in memory, and so on. And we look at this in more detail as well. Okay. And then for each process in your OS, you have a per process file table. And this table tracks what files that process, a specific process, has opened for reading or writing. And here again, you will have an entry to the open file table that tracks where this file is within the open file table. You will have something that's time within that file. That's specific, remember, to each process, because even though multiple processes may have opened this file for I/O, each process is going to have its own offset, as well as the mode in which the process has opened the file, whether it's a read, write, or read write, and then some pointers to the OS buffer. Okay, and remember that last time when I was talking about device drivers and so on, I mentioned that every device is going to have a buffer cache, and the file system in particular makes heavy use of the buffer cache. So the file per process file table is also going to have a pointer to file buffers. Okay? Now keep in mind that these are in-memory OS data structures. So this is what the OS maintains in memory for the file system when it's executing. These are separate from on-disk structures that we are going to look at soon, which are maintained by the file system on disk itself. Okay, so now we can quickly go through some key operations and see how these two data structures, the per process file table and the global open file table, are used to implement certain interfaces. So the first one is create. Okay, so create is a system call. Here we just have a generic name for it, but it's a system call that allows us to create a new file in your file system. So every time you try to save a file and give it a new file name within, let's say, an editor, internally you actually have to create the file first before you can actually save data to it. So create is the system call that gets called for that purpose. So the steps shown in create are listed here. So first you got to check whether there is sufficient disk space for creating a new file, whether the user actually has permissions to create a file within the specified directory, and so on. And assuming all of that is true, we are going to then create a new file descriptor for this file. And the file descriptor, as we will see, is an on-disk data structure. Okay, so it will basically store the name of the file, the location of the file on disk, and other file attributes. And we are going to essentially add the file descriptor to the directory, and then we are going to essentially see whether there are other things to track for the file, which include the file type and so on. Okay. So that's very quickly how a create operation or a create system call is going to get implemented. So essentially you do some checks, and if the checks pass, you basically allocate a new entry in the on this data structure saying a new file has been created. Okay. Now, whether there are some trade-offs on whether the file system needs to keep track of the file type, whether say it's a Word file document or an executable and so on. The advantage of doing this is when you do things like double click on a file, the OS knows what type of file it is, so it can launch the appropriate program. Okay. And it can also do better error detection because you know what type of a file it is and so on, or even optimize the layout for different types of file. Okay. But the disadvantage is now the file system needs to know about every possible file type that exists out there, which may complicate the file system. And if new file types are created at a later point, either the file system will not know about them, or you have to extend the file system to get it to know about them. So those are some trade-offs. Now Unix does not have the notion of a file type. Most file systems in Unix assume that files are a sequence of bytes. There is no type associated with them. Okay? Now even though that is indeed the case, you can still track file types outside the file system. which is what things like X windows as well as the graphical user interface on your Mac do, because the Mac will still allow you to double click on a file and open a particular program to access that file. Okay. Now the delete operation is going to do the opposite of what the create operation does, which is release the space allocated to the file and delete the entry for that file from on-disk data structures. So here, to do delete, you have to first find a directory containing the file. You got to go and release all the disk blocks allocated to the file and put them back on the free list, and then remove the file descriptor from the directory. Okay? And we'll get to ref counts and so on in a little bit, because there are some subtleties associated with delete based on if multiple names point to the same file and so on. Okay. Now let's come to open, close, read and write, which are the key operations the file system actually supports. So when you try to open a file using the open call, you're going to specify the name of the file you want to open and the mode, which is read write. And here you're going to first check, has the file already been opened by some other process, in which case there's going to be an entry in the global file table. If not, you create a new entry. And then you check whether the file protection bit allow you to open that file in that mode. If not, you're going to give an error. Otherwise, create an entry in the per process file table and initialize the pointer to 0, which is offset 0. Okay, and that allows you to open a new file. So you're going to create two entries, one in the open file table, which is global, and one in the per process file table. Okay. And when you close the file, all of these entries essentially have to be removed from the global file table and the per process file table. So the per process file table entry gets deleted. In the global file table, you reduce the ref count or the open count by 1. And if that count goes to 0, that means there are no other processes accessing that file at the current time. So you can delete that entry from the system-wide file table as well. Okay. Now, read and write operations, given that you opened a file, are somewhat straightforward. So when you try to read from a file, which is the random access, what you're going to do is you're going to essentially look for where the data is on disk and read from that location. Okay? But first, you've got to look at whether the data already exists in the buffer cache, and if so, you're going to read it from it. And we talked about this last time, where every I/O operation first looks in the buffer cache, and if it's a hit, you support it from there. If it's a miss, you actually go and read it from disk or write to a disk. So in case of random access, you basically go to a specific location on disk where that offset resides, and then you start reading from there. And in case of sequential access rather, you just look at where the file offset is pointing, and then you go to that location on disk and read from that location. So both of these operations can be supported based on the data structures that you maintain within the file tables and on disk. And write is going to do similar things. So it's going to, rather than reading, it's going to write to a specific location on disk. Okay. You also have a seek call, which allows you to change the file offset to a particular location. Right? So typically seek points to where to read next, but you can actually read from any location or within that file by manipulating seek. Okay? And then I have already mentioned memory mapping before. Just as you can memory map I/O devices, you can also memory map files. When you memory map a file, you essentially take that file and map it to address space with that extends RAM, and that allows you to access that file as if it's basically part of RAM. And then this allows you to read or write to that file as if you're reading or write to memory location, rather than issuing specific read or write code. So the same concepts we used for memory mapping I/O devices also hold for memory mapping of files. Okay. Now, as far as file access methods are concerned, you can have either sequential access or random access to a file, depending on the application. Right? If there are things like databases where you're making queries can access different records, the access pattern may be random. But if you have a compiler that's compiling a file, you're going to read that file sequentially and read that entire file in memory, and then you're going to compile it, and then you're going to sequentially write out the results of the compiled code back to disk. So depending on whether or what kinds of process it is, you will get either sequential access where you're reading the file one byte at a time or one block at a time from the start to the end, or random access where you can access it from any location on disk. Now from a design perspective, you have to support both kinds of access. So the data structures that we are going to maintain on disk to access a file has to be designed so that it will support both sequential and random access efficiently. And soon we are going to look at these data structures and also examine the trade-offs from a perspective of sequential and random access. Okay. Now let's talk a little bit about naming. Okay. So naming essentially means two things. One is how do you access the file using its file name, and then the second, which is related to directory structures, is how are you actually going to organize the file on disk. Okay. Every file has a name. And the full name of the file is essentially the name of the file in terms of how you access it from the root directory. So you might have something like /user, /local, /bin, /chrome. That's the full name of a file, and it basically has the directory structure embedded in it, as we can see. Okay. So there are many naming strategies that file systems provide. The simplest one is single level directory, which essentially means you can't have any directories. There's only one root directory, all files are stored in there. Very primitive file systems would support this. No sophisticated file system is going to support only a single directory. Okay, now the issue in single directory is all file names have to be unique. Okay. If you have directory structures where you have multiple directories, you can have two files named foo in two different directories, and that's okay, but not in a single level directory. Okay? And in multi-level directories, you can have arbitrary organization where you have a tree structure, and you can have directories and they are nested, and you can have other subdirectories in them, you can have arbitrary nesting, and the leaves can all be all files that are stored within that directory structure. Okay? So when you try to open a file, the file system actually has to track that file down by doing what is called a lookup, or where it starts from the root and it descends down the file structure hierarchy until it gets to the specific file we are looking at. And we'll get to that in just a little bit. Okay. Now let me also say something about referential naming. Okay. The typical assumption we have made so far is the files have a name. Okay. And every file needs to have a name. But file systems are also going to allow us to give multiple names to a file. So a file can have more than one name. And this is done using what are called either soft links or hard links within Unix. And in Windows, these are also called shortcuts. Shortcuts are the same as soft link. And you use the ln command to actually create either of these. ln-s creates soft links, and ln creates a hard link. Okay? And as is shown here, let's say your file name A, which is file 100 on your file system. If you do ln AB, that essentially says take the file with the name A and assign it a second name called B. Okay, so now you will get a second. So the file has two names. So when you do an ls, you are going to see if both of these names exist in the same directory. If you do an ls, you are going to see two files, although there are two names that point to actually the same file internally. Okay. Now the interesting thing here is, now if you have two names for a file and you delete A, the entry for A is going to be removed, but the file itself is still going to exist because there is another name for it, B, which allows you to access the file. Only if you remove both A and B will you actually delete the contents of the file as well. Okay? And this is why you need to track within the file system a ref count, which says how many names does a file have. And every time you delete one name, you decrement it, and only when the ref count goes to 0 do you actually delete the file. Now the common case is of course that the file has only one name, so the ref count is typically 1, and when you delete the file it goes to 0 and you immediately delete it. But that need not be the case if the file has multiple names to access it. Okay. Now the thing to keep in mind is these names can also exist in multiple directories. You don't, and this is why you have links or shortcuts to allow you to access the file that's stored somewhere else from another location. Okay. Now one thing I should mention here is the difference between soft links and hard links. Okay, soft link essentially is pointer that tells you that if you want to open a file, go there and look elsewhere. But when you make a hard link, you actually create two entries in the file system that point to the same file. And there are some implications of hard links, also soft links. When you delete, when you have a soft link and you delete the original file, it gets deleted and you might have a dangling pointer, which is a missing shortcut in Windows. But when you have hard links, this does not happen because the file system knows that there are multiple names for a file. You delete a file, it only decrements the ref count and does not delete it if there are other names mapped to a file. Okay. The other thing that is a restriction is you cannot actually have hard links for directories, because this can create circular loops within the file system. If you have a parent directory that's pointing to a root, or a child directory that goes and points to another upper level directory, this might create a loop, and that causes all kinds of problems because the file system hierarchy is an acyclic graph. It's a DAG, so you don't want loops, which will cause problems for things like backup programs because they'll never terminate. They'll just sit in a loop trying to essentially keep backing the same data over and over again. So you can have soft link for directories but not hard links. For individual files, you can create both hard links and soft links. Okay. So those are all things to keep in mind. Now I'm not going to go into directory operations in any detail. Just as you can create a file, you can create a directory, you can essentially list all files in a directory, you can rename a file, and so on. So these are all standard operations that a file system needs to support, but for manipulating directories as opposed to files. Okay. So very quickly, as far as protection is concerned, there are two methods by which file systems allow you to decide which user on that machine gets access to files. Okay. So these are called either access control, to create what is called access control lists, or ACLs. ACL is the acronym for access control list. So what an access control list is essentially a list of user names that have permissions to access the file and what kinds of permissions or rights they have on the file. So for each file you will have a list. By default, that list will have only one entry, which is the owner of that file who created the file. So the owner has obviously access to the file, and depending on whether it's executable or just a source file, you might have read, write, execute access on the file. But you can keep adding entries to this ACL saying this other user has access to the file, and that is going to be used by the OS when you open a file, saying does the user, is he or she present in the ACL, and should I allow that user to access that. So that's the Windows way. Right? Unix does something different. So rather than creating an arbitrary list, it essentially groups users into three categories, and they're called user, group, and world. Okay, so and it keeps 3 bits for each group. So a user can have read, write, or execute permission. The Unix group that the user belongs to, which we can contain many other users, also gets 3 bits. And then you have world. So essentially you divide all users into 3 groups: the owner, the Unix group, and everyone else. And so you have more coarse-grained control than an access control list, where you can specify an arbitrary list of users or arbitrary groups and so on. So it's a more coarse-grained method, but it's more efficient from a storage perspective because you essentially need only 9 bits. Okay, read, write, 3 read, write, execute bits for users, 3 for the group, and 3 for world, as opposed to an ACL which could have arbitrary size and it might take more space. So this is more coarse-grained but more storage efficient. So that's the trade-off. And the meta point here is, using either of these two mechanisms, you can control. So for example, if you don't want to give access to anyone else, in Unix you set the read, write, execute bits for the group and the use and world to be all zeros, which means only you have access and no one else has access. Or you can give access to users within your group and so on and so forth. Okay, now with that in mind, so we have quickly gone through in-memory data structures that the file system maintains, which are the process file table and the global file table, as well as some high-level concepts of how open, close, read, write and all of these things work. So in the remainder of the lecture, I'm now going to switch to on-disk data structure. So this is the complementary part of a file system where we are going to discuss what does the file system do on disk, how does it actually store data on disks and so on. Okay? So in other words, going back to this picture I showed you earlier, we are now going to look at the lower layer, which is the hard disk, and how you can implement a file system data structures on your disk. Okay? So let me show you first how typically magnetic disks work. This is now getting somewhat outdated because most of your computers have solid state disks that don't look anything like what I'm going to talk about, but it's still instructive to see this because there are still plenty of servers that use magnetic disks as well. Yeah. So a typical disk looks like what a CD looks like. You've seen what a CD or a DVD. So it's a circular platter where data is recorded. And this picture here shows us that data is recorded in concentric tracks, concentric circles called tracks. And each track is divided into smaller chunks called sector. A sector is the smallest unit of data that you can read or write from a disk. Okay, so you will basically, so tracks are going to get numbered. So maybe the innermost track is 0 and the outermost track is n. So to address something on a single platter, you specify the track number and then you specify a sector number within that track. So you say track 5 and sector 7. So within each track, the sectors are going to be numbered 0 to n. The tracks are also numbered 0 to n, going from the innermost track to the outermost track. And typical disk is actually going to have more than one of these platters, as is shown in this picture. So think of them as a stack of CD-ROMs. All of them are spinning. So you essentially also have the platter number, which is called a cylinder. So you essentially will have cylinder and then track number and then a sector number within the disk. Okay. So typical access to the sector on a file is going to involve some overhead, because you have the disk head, this platter is spinning and the disk head is positioned at a certain location, which means that it's going to be positioned on a certain track. So if you want to read data elsewhere, you have to mechanically move the disk head to another track. That's called the seek time, and the time to actually move the disk head to another track or a cylinder. Okay? And once the disk head is positioned on the right track, you still have to wait for the sector to spin by and come under the disk head when you can read or write to it. That's called a rotational latency. And then your transfer time, which is when you're actually reading or writing. Okay. All the time spent in doing seeks and rotations are wasted time, because the disk cannot actually do any I/O. It is simply trying to move the disk head to where it needs to be to actually do I/O. So many file systems that are designed for magnetic disks are going to spend some effort in trying to reduce the seek and rotational latency, and this is done by efficient layout on a file of the files on disk to reduce your seek and rotational latency. Okay, so that's something we want to keep in mind. Now, none of this is going to apply to magnetic disks, because switching to another block is instantaneous. It's like going and reading to another location in RAM. There is no overhead regardless of how far the next location is with relation to the current location. In magnetic disks, the further away the next sector is from the current location, the more the seek time and potentially the rotational latency, and the higher the overhead. In SSDs and are similar to a RAM, where there is no such overhead. So many of the optimizations that file systems have performed for hard disks no longer apply to SSDs, and SSD file systems can be designed differently, because some of these overheads don't exist, and you don't need to account for them. Okay, so with that in mind, let's look at how files are organized on disk. So essentially, for every file, you're going to have a table, and that table is going to track where blocks of the file are stored on disk. So you will say each file is going to be numbered. So let's say you have file 0, you say where is block 0 stored, and you have an address which says it's on platter 0, cylinder 0, sector 0, and block 1 is on platter 4, cylinder 3, sector 8, and so on. Okay, again, like in memory and process layout, we can have disks that are contiguous or not, which is why you need this table to track where the files are stored. So this file table is similar to a page table for a process. Page table tracks where the pages of a process are stored in RAM. The on-disk file table tracks which we'll refer to as an inode in just a moment, or a file descriptor, tracks where the blocks of the file are stored on. So they are similar concept. Okay. Now remember that last time I also mentioned that you can have logical block addressing, where rather than using this triple of platter number, cylinder number, sector number, you can just uniformly address the blocks from 0 through n and then translate it internally to this triple. So you can use either of these two addressing mechanisms in your file table. Okay. So now the question is, how are we going to lay out our files so that they support sequential and random access efficiently, so that you can figure out where the blocks are on the file and so on. Okay. So to do this, we need a key data structure for every file that is stored on disk, which we'll call the file descriptor. Okay. This is separate from the per process and the global file table. Those are in-memory data structure. This is an on-disk data structure. So for every file you store on disk, you are going to have a file descriptor. Okay. File descriptor is going to track all the information that you need to access that file from disk. So it is basically the metadata structure for the file. Okay, the file has data, which is the contents of the file, and the file descriptor is metadata for the file. Okay. Now to efficiently store the files on disk, we make a couple of observations, which is that most files are going to be small. The mean file size of files on disk is still between 4 and 8 kilobytes. But most of the storage space is taken by a small number of large files. Okay, so there are lots of small files, but and they don't actually take a lot of space in the aggregate, but most of the space is taken by a small number of large files. So what this means is you need to provide good access to both small files and large files while optimizing for the common case, and the common case is that files are actually small. Okay? So you want to allow sequential and random access. You want to make sure that you can access small files efficiently as well as large files, maybe as somewhat efficiently. Okay? So we'll look at 3 different layouts here for how you store your files on disk. The simplest one is contiguous allocation. So this is like what you had in for process allocation, where you allocate a chunk of disk space and the file is stored contiguously. So here all you need to know is the starting location of the file on disk, the starting address and the size of the file. So because all the blocks are stored contiguously, once you go to the start location, you can just access all the blocks without any additional information. So the file descriptor just needs the start address and the size of the file. Okay. So it's a very simple organization. Okay. It is going to allow us sequential and random access, because once you know the start address, you know where the fifth block is stored, which is 5 blocks from the start location of the file and so on. And sequential access is also fine, because you're going to just do one seek and just read that entire file from starting to the end. Okay, so both seek and sequential and random access are efficient. The problem though is that this can cause disk fragmentation, just as contiguous allocation in memory caused in-memory fragmentation. So if the file grows and there is no space to grow because you stored another file right next to it, then you are going to have to move the file or give an error. So you have all the problems that occur when you have fragmentation. Once you start adding and deleting files, you're going to have holes and so on. Okay. And this is addressed to disk defragmentation programs that are going to go and move files around to reduce fragmentation. All of them impose overheads. Okay. Now contiguous allocation, although it's a very simple method, is not used in sophisticated file systems just to avoid the fragmentation issue, but they're still used in things like CD-ROMs and DVD-ROMs, where you only write once, so there's no fragmentation. So if you're trying to create a DVD and write a bunch of movie files, just write them sequentially, one after the other, because these are write once devices. You don't delete any files once you write to them. So it's fine to use this simple allocation. It's efficient and it's simple to implement. Okay. Next organization is a linked list. So you keep files as linked list, where each block of the file has a pointer to the next block. Okay, and that's shown in this picture here, where your file descriptor that has the pointer, the head pointer to this linked list, which is the first block of the file on disk. And you see the address at the last location on the file descriptor. And then you, in the block of the file, you store data, but the last byte or two of the file, or 3 bytes in this case, or three words, are going to essentially have a pointer to the next block and so on. Okay? So that's an organization. It is actually used by some primitive file systems as well, such as the DOS early file system used a linked list organization. Okay? Now, as you can imagine, in this case, sequential access is fine, where you access each block and then you have a pointer to the next block and so on. But random access is not going to be efficient. Now, just as in any linked list, if I say go access the ith location of that list, you have to start from the head and sequentially scan through the linked list until you get to the ith location. So random access is not going to be efficient here, but sequential access is fine. Okay? And to access all n blocks sequentially, you're going to incur n seeks, because the blocks are no longer assumed to be contiguous, and you've got to go through each block to access the next block and so on. Okay? Now, there's no fragmentation in this case because any block can be anywhere, so you got rid of the fragmentation problem. You can increase the size of the file by just adding entry to one more block in the linked list and so on. Okay? All right. So the last organization that we want to discuss here is the indexed organization, where you essentially have an index, which is a table, and it has pointers to blocks on disk. Okay, so that's a simple single level index is shown here. It's essentially an array where you want to access the ith element, you go to the ith location in that index, it gives you a disk address, you go to that location, read the block, and you have the ith block of the file. Okay. So this is an organization that's going to allow us efficient access to both sequential and random access to a file. And all you got to do is read the file descriptor into memory, and then essentially the index looks like an array. You can scan it sequentially and read blocks, or you can just go to any location I in the index and get the ith block. Okay. Now, one issue with the indexed organization is that file descriptors are pre-allocated by the file system when you format the file system at file system creation time. So when you create a file, you have to allocate this descriptors, and you have to decide how large that index needs to be at creation time. And since files can be of arbitrary size, you don't know ahead of time how big any particular file is going to be. So this file descriptor has to be pre-allocated to be large, and the size of the entries in the index also determine the maximum file size. Okay. Now, since I already mentioned most files are small, allocating a large index for every single file, or pre-allocating a large index for every single file, is going to be enormously wasteful, because all these entries in your file descriptor are going to be wasted. Okay? But you have no choice but to do that, because you don't know ahead of time how large that file, any particular file might be when the user creates them at a later time. So to address this issue, systems do is a multi-level index. Okay? This is in UNIX terminology called an inode, okay, or an index node, where you basically have a multi-level index structure. Okay? So as is shown here, the file descriptor only has 12 entries, okay, or rather 14 entries. Okay? The first 12 entries of that file descriptors are direct pointers. They point to disk blocks that are going to be part of that file. If the file is larger than 12 blocks, then the 13th entry is actually a pointer to an indirect block, which has another 1024 entries, as is shown here. So that's called a single level indirect block. And if the file grows beyond 12 plus 1024 blocks in size, you use the 14th entry, where you point to a block, each of those blocks point to another block, and those are the ones that have pointers to blocks. So there are 2 levels of indirection. So these are called a double indirect. And modern file system have a 15th entry, which is a triple indirect block. Okay? So the reason this is more efficient is because most files are small. You are never going to use the 13th and the 14th entry of the file descriptor. Maybe you are going to be okay by just using the first 12 entries. So all you need to do is read the file descriptor, and most of the contents of the file you can access to the first 12 entries, because most files are going to be either 1 or 2 blocks in size, as we saw. But since some files are large, You can also support larger file sizes by using the single indirect, the double indirect, and the triple indirect blocks of the file. Okay, so this is how the inode structure is created, and the important thing is only the file descriptor is pre-allocated. Okay, so only the 15 entries of that array are pre-allocated. The single, double, and triple indirect blocks can be allocated on demand, just as you allocate blocks to any file. You can also allocate these blocks to the file descriptor. So you never waste any space by pre-allocating a giant structure for large files. Okay, so this is a multi-level index. It supports incremental file growth. It's efficient for small files, but it's also reasonably efficient for large files, because you'll just have either 1, 2, or 3 levels of indirections. That's still not bad as a linked list where you have to essentially scan linearly through a file. Okay, so it's some less efficient for very large files because the level of indirection grows, but it still supports it with no more than 3 seeks and 3 rotational latencies, because to get to a block in a large file, you will have at most read the file descriptor, read the single, double, and triple indirect blocks to get the address, and then you can read the block. Okay? The file size is still bounded by the maximum file size is still bounded by the number of entries you can store in this multi-level index, which is going to be 12 plus 1024 plus 1024 square plus 1024 cubed. Those are the number of entries, max number of entries you can store in this structure. Okay. The last thing I want to say here is how does the file system know which blocks are in use and which blocks are not in use or free, and this is done through free space management. So you can essentially do the same thing as what you did for tracking free pages in memory. You can have a bitmap, one for each sector of the disk or block of the file, where 0 says that that sector is available, 1 says it's not, and so on. So if you want to now allocate a new file, you can scan through this bitmap and look for some chunks of zeros. So you can create that file. You need only 1 0 to allocate one block. But if you want to create a new file, a heuristic might be find a region where there are a chunk of free blocks, so that you can store blocks of the file close to one another. And they don't have to be contiguous, but the closer they are, the lower the seek overhead. That's not an issue in SSDs, but still a good heuristic for normal files, for a magnetic disk file system. Okay. Now, in a free delete a file, the blocks are basically marked free in the free block list, okay, this bitmap. And when you allocate blocks to file, you're going to scan and find entries that are unallocated and turn them into one and allocate them to a file. Okay. Now, one thing is the bitmap itself might be too large to keep in memory. Okay. A very small 2 GB disk, which is like a USB thumb drive, might have as much as 4 million entries, and if you have 2 TB, that is 3 orders of magnitude larger than. So you don't want to keep gigantic bitmaps in memory. So what file systems will do is they will partition the bitmaps into zones of a file or regions of the disk rather than a file, and then only bring them into memory as needed. So this is one way by which you can reduce the amount of memory needed to keep that entire free block list in RAM at all times. Okay. The last thing I want to mention is a picture of what the disk looks like. Okay, so here we basically ignored the circular structure of a magnetic disk, and we are using logical block addressing, and we addressed the blocks from 0 to 127. And as you can see here, block 0 is typically called the super block. Okay? The super block keeps metadata for the file system, and you'll see here it has the free block list. This is a toy file system where you only 127 blocks, so there are 128 entries, and then there are inodes that you have pre-allocated in the super block. Okay, typically, a real file system will have more than one super block because you pre-create a large number of inodes. Okay, the max number of files is determined by how many file descriptors you allocated at format time, and so you'll have multiple super blocks at multiple locations on disk that have stored all of these inodes in them. Okay, here you have only one, but you will have more than one. Okay, so your super blocks and regular data blocks. So anything that's not a super block at creation time is marked as with a 0, saying it's a data block and it's available for use. And as you create files, you are going to start using this inode entries, okay, up for allocating them for new files, and then you are going to start using your blocks on disk to allocate data storage space to each file. Okay. Directories are also stored in the same fashion. Every directory has an inode, because from Unix perspective, a directory is just a file, but it's a special file where it has a table of other files contained in it. So the data blocks of a directory will actually have pointers of file names and their inode numbers. Okay. So they are stored in a similar organization. Okay. So this is a picture you want to keep in mind for your on-disk data structure. Okay, this is how a typical disk layout is going to look like, and then everything that you have inside or in RAM are other data structures like the process file table and global file table and so on. Okay. So with that background, I'm going to end the lecture for today, and what I'm going to do in the next class is to talk a little bit about the UNIX file system. How is it organized on disk, how the inodes within UNIX work, and so on, as well as the UNIX file server process, which is now called the virtual file server process, that tells us how UNIX actually implements a file system in the kernel itself as a user space process, rather not in the microkernel, but within the OS as a user process. So let me stop here for today.